We have to find the electric field at any inside or outside point of a solid sphere which is totally uniformly charged. So for this we first of all draw a solid sphere with the charge density constant rho. So this is the sphere of radius a, and now we have to find the electric field at any inside point of the distance r from the origin. So first of all we draw a Gaussian surface at a distance r from the origin. The distance is r. Okay. Now using Gauss theorem, that is the Gauss theorem, we can easily find out the electric field at any inside point. By Gauss theorem we can write that integral of E dot ds, that is equal to charged enclosed by the Gaussian surface by epsilon naught. Now this given is Q prime, this charge enclosed by this Gaussian surface. Okay. Now for this term we can write that E dot ds vector is equal to E ds cos theta. Theta is the angle between E and ds, that is E ds is theta, angle between E and ds. And you can see that from this figure the direction of E is outward and the direction of ds is also outward along the radial vector. So theta will be 0, so that is cos 0, and that is equal to EDS. Okay, now we put the value, that is EDS, that is equal to the Q prime, that can be written as the charge density into volume, because it's a solid sphere, so charge density into volume enclosed by the Gaussian surface, that is this. So we can write this as V prime by epsilon naught. Okay, now here is uniform, so it can be written as constant, so it comes out of the integration. Okay, that's equal to rho V prime by epsilon naught. Now the value of the integral ds is the total surface area of the Gaussian surface, so that is equal to 4 pi r square, that's equal to rho, and the value of V prime is the volume of the Gaussian surface, that is 4/3 pi r cube by epsilon naught, or E equal to. Now we have to find the value of rho. For this we can see that the total charge enclosed by the total sphere or the original sphere is equal to Q, that's equal to rho into the volume, that is 4/3 pi a cube. A is the radius of the original sphere, so from this rho is equal to Q by 4/3 pi a cube. Now we have to put the value of rho in this case, so it will be Q by 4/3 pi a cube into 4/3 pi r cube by 4 epsilon naught into this 4 pi r square term, so it will be 4 pi r square. Now this is equal to, here this and this is cancelled out, and this cancelled out with r square, and the remaining there, that's equal to Q r by 4 pi into this epsilon naught and this a cube. Thus we get the electric field, and the direction of the electric field, that is the vector, is along the radial vector, so it will be r cap. Now we have to find the electric field at any outside point of the solid sphere. For this, at a distance r outside of the sphere, So first of all we draw the sphere of radius a, and now take the Gaussian surface at a distance r from the center or origin of the sphere. This distance is r. Okay, now using the Gaussian theorem again, we get that there is the Gauss theorem. Okay, integral E ds equal to charge enclosed by epsilon. Here the charge enclosed by the Gaussian surface is equal to the charge, that is charge enclosed by the Gaussian surface is equal to the charge enclosed by the original sphere, because there is no charge in the internal or this internal points, so this is equal to q. So equal to integral ds, that is equal to q by epsilon naught, because E is constant. Okay, or E, the value of ds, that is equal to area of the Gaussian surface, that is 4 pi r square, equal to q by epsilon naught, or E, that is equal to q by 4 pi epsilon naught r square. This is the value of the electric field, and the vector E vector is along the r cap. So thus we get the electric field at any inside or outside point of a solid sphere that is uniformly charged.